Module 1, Probability Fundamentals and Common Distributions. 1. Introduction to Probability and Random Variables. Let's start at the very beginning. Probability is the mathematical language of uncertainty. It is how we make sense of situations where outcomes are unpredictable but still follow patterns. A random variable is simply a quantity whose value is not fixed but depends on chance. It can be discrete, meaning it takes specific, countable values, for example, the number showing on a road die. Or it can be continuous, meaning it can take any value in a range, for example, the exact height of a tree. When we combine the concept of probability and random variables, we gain powerful tools for prediction, analysis, and decision-making in everything from engineering to medicine to economics. Key concepts in probability. Experiment, any process that produces an outcome, like tossing a coin. Sample space, the set of all possible outcomes of an experiment. Event, a specific set of outcomes we are interested in. Probability of an event, a number between 0 and 1 that represents how likely the event is to occur. There are 3 fundamental rules, or axioms, of probability. The probability of any event cannot be negative. The probability of all possible outcomes together must add up to 1. If 2 events cannot happen at the same time, the probability of either one happening is the sum of their individual probabilities. 2. The uniform distribution. The uniform distribution is the simplest type of probability distribution. It describes situations where every outcome is equally likely. For example, rolling a fair die, each number from 1 to 6 has the same chance. Choosing a point at random on a line segment, every position is equally likely. The uniform distribution is used when we truly have no reason to prefer one outcome over another. In the discrete case, each outcome has the same fixed probability. In the continuous case, the height of the probability density is constant across the range. 3. The exponential distribution. The exponential distribution models the time between random events that occur at a constant average rate. Examples include the time between arrivals of buses at a station, assuming buses come randomly. The time until a radioactive atom decays. A key feature of the exponential distribution is the memoryless property. This means that the probability of having to wait an additional certain amount of time does not depend on how long you have already waited. This distribution is very important in reliability analysis, queuing theory, and survival studies. 4. The normal distribution. The normal distribution, also called the Gaussian distribution, is probably the most famous distribution in all of probability and statistics. It describes many natural phenomena because of the way random effects tend to combine. It is shaped like a symmetric bell curve and is described by 2 parameters. The mean, which determines the center of the curve. The standard deviation, which determines the spread of the curve. One well-known feature is that roughly 2/3 of the values lie within one standard deviation of the mean, about 95% within 2 standard deviations, and almost all within 3. The normal distribution is so important because of a fundamental principle called the central limit theorem, which we will cover in Module 2. 5. The gamma distribution. The gamma distribution is a continuous probability distribution that extends the ideas of the exponential distribution. It is often used to model waiting times until a certain number of events have happened. For example, waiting until the 3rd customer arrives at a store. Total rainfall in a rainy season. Insurance claims over a period of time. It has 2 main parameters. One that controls the shape of the curve, and one that controls how stretched or compressed it is. When the shape parameter is equal to 1, the gamma distribution becomes exactly the same as the exponential distribution. 6. The beta distribution. The beta distribution is defined only between 0 and 1, making it perfect for modeling proportions and probabilities themselves. It is very flexible, depending on its 2 shape parameters. It can take many different forms, from uniform, to U-shaped, to strongly skewed. Some uses of the beta distribution include representing our uncertainty about a probability in Bayesian statistics, modeling the proportion of a day spent on a certain activity, expressing the fraction of defective products in a shipment. Because it is a conjugate prior for the binomial distribution in Bayesian analysis, it is a favorite tool for statisticians who update beliefs as they gather data. 7. conditional probability. In many real-life situations, knowing that one event has occurred changes the probability of another event. This is called conditional probability. For example, suppose that 5% of emails are spam, and most spam messages contain certain words like free or win. If you know that an email contains the word free, the chance that it is spam changes. It is no longer just the 5% base rate. Conditional probability is a way of updating our knowledge when new information becomes available. 8. Bayes theorem. Bayes theorem is a special rule for reversing conditional probabilities. It allows us to calculate the probability of a cause given an observed effect by combining our prior belief about the cause, the likelihood of observing the evidence if the cause is true, the overall probability of the evidence. A common example is medical testing. If a test for a rare disease comes back positive, Bayes' theorem helps us figure out the actual chance the person has the disease, taking into account the rate of false positives and the rarity of the disease. This principle is at the heart of many modern applications, from spam filters to diagnostic systems to machine learning models.